Hello everyone. In the last couple of videos, we've been talking about arrays as if they're all one-dimensional, but that's not the case. Many applications require you to use a two-dimensional array in order to solve a problem or store some data. So in this video, we're going to talk about 2D arrays. We're also going to talk a little bit about ND arrays or n-dimensional arrays, but our focus will primarily be on 2D arrays. So far, our 1D arrays, we visualize something like this. So on and so forth. For a 2D array, your go-to visualization is something that looks like a grid. Something that looks like this. For 3D, you can think about a cube or something that looks like this. For 4D, I really can't draw it, but you can see how you can keep adding dimensions. The number of dimensions you add is up to you as your programmer. You as the programmer, you want to try to keep it as simple as possible because as you start to add more and more dimensions, as you can imagine, things start to get pretty scary pretty quick. So you'll definitely want to try to keep it down in the 1D, 2D, 3D range because that's where we're really good at visualizing what the data in our array looks like. Let's head over to the notes for today and start working on the warm-up task so that we can get a scaffolding in place in order to code up some 2D related code. The file that we're going to work with today is called 2darrayfun.cpp. Okay, before we start writing code, let's motivate 2D arrays a little bit and then get some intuition behind how they're represented and how we can use them in C++. First off, you can think about many applications that would require 2D arrays. For example, if you take a look at Excel and a sheet in Excel, it looks a lot like a 2D array. We've got a grid here, right? We've got rows going down the left side, columns going across the top, and we can enter data in each one of these cells. This is a good analogy for a 2D array in C++. So I don't want to say any problems that you can think of to solve in Excel would have a corollary for solving with 2D arrays in C++, just because I can't think of all possible things you might want to solve in Excel, so I don't want to make a blanket statement. But you can really think about anytime you've opened up Excel to do some kind of data crunching using a sheet like this, that would be an application of using a 2D array in C++. Other examples of when you might use a 2D array in C++ include coding up anything to do with matrices. So those of you who have taken a linear algebra course, you know about how important matrices are. Things like matrix computation or transformations, rotations, things like that. You could use C++ and arrays in order to code up matrices and write algorithms to traverse them and implement these transformations or rotations, etc. The last motivating piece that I'll give is coding up any game where you have a grid. For example, if you were to play the game of tic-tac-toe, you typically draw a 3x3 board that looks like this, and then players take turns trying to get 3 in a row, etc. We're going to code this up actually today in this video using a 2D array, but this is just a simple example. There are a lot of games out there that use two-dimensional grids in order for the users to play. You can also think about three-dimensional grids and how standard those are nowadays in modern video games. Those three-dimensional landscapes that you can run throughout or explore, those are all based on usually a coordinate system that has some kind of underlying representation as an array or a matrix. Okay, so let's get started now talking about the intuition behind 2D arrays. I like to think about 2D arrays in two different ways, and I want to present those two different ways to you, and hopefully they'll both click, but maybe one will click more than the other, and that will be what you use in order to help you understand 2D arrays. So the first way is to think of a 2D array as a nested array. That is, a 2D array is really a 1D array where each element is an array. So let's take a look at an example. Let's say we have a 2D array of integers called myints, short for myintegers, and we've declared this to be 2 by 3 in size. I can also initialize this array at the same time that I declare it by using curly braces. So the first curly brace is for the 1D array. Each element of the 1D array is also an array. So I need another curly brace for the first element of my 1D array. And since I've specified that there are 2 elements in my 1D array, and each element itself is an array holding 3 items, then I've got to put 3 items in here. So let me color code this to help it make more sense. So the 2 here is the number of elements in the 1D array. So that's why there are 2 elements here. Index position 0 is this array. Index position 1 is this array. The red here is the number of elements in each array element, referring to the green. So we've got 0, 1, 2, 0, 1, 2. Those are the valid indices of our nested arrays. This array is nested in this array, and this array is nested in this array. We're familiar with the term nesting or nested from our background with if statements and loops. So if thinking of a 2D array as a nested array, then if thinking of a 2D array as a nested array helps you because you can think about putting loops inside other loops or if statements inside other if statements, putting arrays inside other arrays. That's awesome. Here's a second way of thinking about 2D arrays. A 2D array as a grid of rows and columns. And you can think about that Excel sheet that I just showed you as a good application of a grid of rows and columns. When you think about it this way, this array visually looks like this. On the left side, we've got rows, indices 0 and 1, and on the top, we've got columns. 0, 1, 2. So for example, 3 is at row 0, column 2. We could also figure this out by using the nested approach. Array 0, sub 2. 4 would be at row sub 1, column sub 0, row sub 1, column sub 0. Okay, so let's head over to the code then and code up my ints so we can see it in action. Now we can save and compile this, but if we run it, nothing's going to happen because we don't have any cout statements here. So let's go ahead and write a function that's going to print a 2D array. So we'll call it print array, which we could overload our other print array functions that we may have written, but this one is going to accept a 2D array of integers, the number of rows, and the number of columns. Right now I'm using 2 and 3 hard-coded. I think it would be more helpful if I declared these as constant integers. So we'll call it rows and columns. Now we can go ahead and replace these hard codings with our variables. Now we've got to declare our prototype. So this is a 2D array of integers, so we have 2 hard brackets, and then int, and then int. I do have to make one comment here before we move on though. The compiler needs to know the size of all dimensions except the first. So when we've been passing in 1D arrays into functions, we haven't had to put a size in the hard brackets in our definitions or in our prototypes. But with n-dimensional arrays, the compiler does need to know the size of all dimensions except for the first. So that means we have to put the calls in here, otherwise our code won't compile. We can also put the rows in here, that's optional, but typically I won't put the first one in there just because it takes a little more time to code, and if something gets changed later, it's one more thing that has to be changed. But the compiler has to know the calls, the columns, and the reason why has to do with the offsets. Remember we drew that diagram on the board where we saw the memory addresses for each of the locations in a 1D array? Well, in a 2D array, the compiler needs to know how big the rows are in order to figure out the memory address for an item. So essentially that's what we're telling the compiler here. How many items are there in a row? All right, now we're ready to code up this function. Print array is not going to modify the array at all, so I'm going to put a const in front of the parameter declaration. Okay, so when we were working with one-dimensional arrays like this one, we had a single for loop that we used to grab each element. Now with a 2D array like this one, we're going to need a nested for loop because we need a loop control variable to tell us which row to grab, and we need a loop control variable to tell us which column to grab. Hence, a nested loop. So we'll need an I and a j, where I is used as the row index and j is used as the column index. Zero-based indexing, as always. So for I as our row index, we want to run it from 0, stopping at rows, the parameter. J is our column index. We want to start it at 0 and run it to calls. One note to make about this lowercase calls here versus this uppercase calls here. Our uppercase rows and calls is the maximum dimensions of our array. Remember, we could partially fill it, just like we've been partially filling our 1D arrays. If it's partially filled, then we definitely want to make use of our parameters that store the actual number of rows and the actual number of columns that are filled in our big rows by big columns maximum amount of space. So in a 1D array, if we wanted to get a value, we would subscript using the hard brackets one time. With a 2D array, we've got to subscript twice. And for an ND array, n times. So let's print out array sub I sub j. And I'll put here index twice because it is 2D. Oh, and I've got to change my prototype to also be const. There we go. All right, so we're able to print out all 6 of our values, 1, 2, 3, 4, 5, 6. While this output is okay, it would be better if we could print it out in this kind of grid structure that you see here. So I'm going to give you a task. Change the nested for loop so that it prints the output in a grid-like structure. It doesn't need to have lines or anything, but I do expect the 1, 2, 3 to be on one line and the 4, 5, 6 to be on the next line. See if you can figure out how to get it to print that way. The first thing that we're going to do is remove this endl and replace it with a space. Then that will put them all on the same line. But I want there to be a new line character right here. So this new line character should appear after we process all of the items in a row. We finish processing all of the items in a row after this for loop. And then just for good measure, I'm going to put another endl outside of the whole for loop, so there's another space. And there we have it. We've got our nice grid-like structure now that matches the model that we drew on the board. Okay. So we've talked about declaring 2D arrays, and we've talked about how we can print them out, either flat or as a grid-like structure. Now I want to code up an actual example problem. We've been working with our myInts integer 2D array, but let's try working with something that's a little more tangible and represents a real-world problem. So let's code up a board that represents a tic-tac-toe board. Tic-tac-toe is a 3x3 grid of chars. Typically the chars are X and O that the players use, and then just empty space to denote that the cell is unoccupied and a player could place an X or an O there. Let's go ahead and code this up, but instead of just blank spaces, let's use B to denote a blank. That way we can at least see the B's when we print out our board. All right, so we're in main. Let's go ahead and declare a char array called board. And we should put a size in here that's a constant. So let's have const int TTT size. TTT is short for tic-tac-toe. And let's set it to 3. Some tic-tac-toe boards are larger than 3. So if we use this constant in our code instead of 3, we could easily come back and change it later to make our board bigger. Let's not initialize our board at the time of declaration. Let's instead write a function that initializes the tic-tac-toe board to all blanks. That is all capital B's. Go ahead and pause the video and try this. Just like 1D arrays, 2D arrays are passed by reference. So I feel confident that you can write this function. We can pass in rows and columns if we would like to initialize board, kind of up to the programmer preference, because we know that a tic-tac-toe board is not going to be partially filled. So I'm going to go ahead and still pass them in for good practice, but just make a note that rows and columns are optional. In fact, we could assign default arguments here to force them to be optional. For example, if a rows and columns is omitted for our initialize board function, by default, we could just set them to be size if we want. This is a good application of default arguments. So I'm going to be a lazy programmer, and I'm going to go ahead and just copy print array and paste it here. Then I can just go ahead and make my updates to make this initialize board. Take off the const int. This function is definitely going to modify memory, so we can't have it be const, and it's not a 2D array of ints, it is a 2D array of chars. I'm going to remove the cout statements because this function isn't going to print anything. It's going to simply assign to array sub I sub j the character E. All right, we are ready to call this function. And I'm just going to pass in board. I can omit the rows and column sizes because we're using the default arguments. Cool, so I run this. I don't have any output related to my tic-tac-toe board, but it looks like everything seems to run smoothly. So that brings us to our next task. Write a function that prints the tic-tac-toe board. And for good practice, go ahead and overload the print array function to do this. It'd be a good application of overloading. So we've already solved this problem, but for a constant integer array. Now we need to solve this problem, but not for a constant integer array, but for a constant char array. That's all we need to change there. Then we need to add a prototype for our overloaded function. And then we can pass in our print array. Note that currently we haven't used default arguments for our print array. We can if we want, or just to be consistent, we can require that the programmer has to type them in. And there we have it. There's our tic-tac-toe board with all B's. So let's take this one step a little bit further, and let's prompt the user for a row and column coordinate pair that represents where they would like to place an X. So we're essentially coding up a little bit about how we would actually play this game. We'll get this coordinate pair from the user, and then we will update that location to be an X. Go ahead and pause the video and try this out now. And there we have it. I said I wanted to place my symbol at 2, 1, so that'd be row 0, 1, 2, this row, column 1. Column 0, column 1 is this one, and there it is. There's an X placed there. So something to work on from here would be finishing the tic-tac-toe game. You also might want to add some sort of input validation so that when you prompt the user for their row and column coordinates, you first of all check to make sure that they're in bounds, and then you check to make sure that there isn't already a symbol there. And then you could have a do-while loop that would run the game until someone has 1. This would be a really, really great practice that would bring together a lot of the concepts we've covered in the course so far. In the notes for today, I have some additional practice that you can take a look at. For example, practice with indexing. Here's an example tic-tac-toe board, and here are some Boolean conditions that all evaluate to true. Make sure that you understand why they all evaluate to true. Here's another example that uses a matrix. This is a slightly larger 2D array than the my-ints we worked on the whiteboard. This one is a 3 by 3, and here's a nice visual representation of that 3 by 3 matrix. And here are some examples indexing into that 3 by 3 matrix. Here's some code that loops through matrix, and it prints out both I and j values as well as the value at row I, column j. And then down here for 2D array arguments, it shows another example of the display or print array function, where you have to specify the size of every dimension of the array except for the first. And then in closing, at the very end, I want to talk a little bit about ND arrays. What we worked with today are 2D arrays, and what we've worked with previously are 1D arrays. For ND arrays, it's the same as 1D and 2D, except you just have to add another pair of brackets for every additional dimension. For example, to declare a 3D array, you'd have to have 3 subscript notation brackets with 3 sizes. And then to index into a 3D array, you would have to have 3 subscript brackets with 3 indices. And if you were to write a for loop, for example, to iterate over a 3D array, you would have to have a triple nested loop where your outside loop, say I, index into row. The next inner for loop has a loop control variable called j, which index into a column, and then you have a third nested inside for loop, maybe with a variable called k that's used to index again in order to get your actual value. So for a 3-dimensional array, you would have 3 loops, 4-dimensional array, 4 loops, so on and so forth. But really, the moral of the story is try to keep it simple, try to keep it to 1D, 2D, or 3D if you can, because being able to visualize it like we can with our grid or our cube or our linear structure is very, very, very important.